Welcome to our quantum deep dive.
Great to be here.
Today, we're diving straight into, well, a pretty fascinating field, quantum imaging.
Absolutely.
And we're drawing our insights mainly from Jürgen Schneppat's essay, Quantenbildgebung, Präzision durch Quantenphysik.
That's the plan. It's a great overview.
Our mission, really, is to try and unpack how these, frankly, bizarre quantum rules can let us create images, gather information in ways that, classical physics just can't.
Right. And for you, the learner listening in, this deep dive should give you a clear sense of the core ideas, the really exciting applications people are talking about, and where this tech might be heading.
Without getting totally lost in the weeds, hopefully.
Yeah, exactly. We're pulling out the key insights from Schneppat's work, trying to give you a solid feel for why quantum imaging is generating so much, buzz.
Okay, so we're grounding this in Jürgen Schneppat's essay. It covers a lot, from the basic quantum stuff right up to the latest tech and its impact.
It really does. A comprehensive look.
We'll try and highlight the most intriguing bits for anyone curious about, maybe, the next big revolution in imaging.
Sounds good.
So let's kick off. Fundamentally, what is quantum imaging? How is it actually different from, say, my phone camera or an X-ray?
Okay, yeah. So at its core, quantum imaging is all about using quantum mechanics, the physics of the very small, to generate images or get information about something.
Right.
And the big difference compared to classical methods like cameras or X-rays is how it works. Classical imaging uses macroscopic effects, lots of light bouncing off things or X-rays passing through. But these methods have limits. How small a detail you can see the Rayleigh criterion is a classic example of that limit in optics, or how noisy the image gets if the signal is weak or scatters a lot.
So you kind of hit a wall with conventional techniques. There's only so much detail you can get.
Precisely. You hit fundamental barriers. Quantum imaging, though, gets around these by tapping into quantum effects. Well, it uses things like special quantum light sources, maybe entangled photons, which are like linked particles that share properties no matter how far apart they are.
The spooky action stuff.
That's the one. And it uses detectors that are super sensitive, like they can count individual photons, individual particles of light.
Wow.
And by doing this, using these quantum resources, you can pull out information or build an image with detail and sensitivity that classical methods just can't reach. It's like getting past those old limits.
A new way of seeing, almost.
I'll say that, yeah.
And Schneppat's essay, it stresses this isn't just one field doing this in isolation, right? It's very interdisciplinary.
Oh, absolutely. That's a key point. Quantum imaging really lives at the crossroads of several fields.
Aye.
Well, obviously physics is central understanding and manipulating these quantum phenomena, but then you absolutely need computer science.
Let's create the data.
Exactly. Developing the algorithms to process the often quite complex data that comes out of these systems and to actually reconstruct the images. It's not always straightforward. And then there's the application side. Medicine is a huge one, using this tech to potentially improve diagnostics, make things less invasive. So yeah, physics, computer science, medicine, they all have to work together.
That collaboration must be driving things forward pretty quickly then.
It really is.
Yeah.
The progress relies on advances in all those areas.
This sounds quite advanced, but I imagine the ideas have been building for a while. Can we trace back the history a bit? What were the key steps?
Sure. Yeah, the journey really starts way back with the birth of quantum mechanics itself, early 20th century.
Planck, Einstein.
Exactly. Planck, Einstein, Bohr, laying down the fundamental theories about light and matter being quantized at the microscopic level. But for imaging, a really pivotal concept is photon entanglement.
Right, the spooky action again.
Yeah, introduced conceptually by Einstein, Podolsky, and Rosen back in 1935. They pointed out this weird connection.
But it was just theory then.
For a long time, yes. It wasn't experimentally confirmed convincingly until much later, notably by Elaine Aspect and his team in the 1980s. That confirmation really opened the door to using entanglement as a resource.
And how do they, write that down mathematically?
Well, a simple entangled state of two photons, say their polarization, could be written as something like psi equals 1 over root 2 times the state 0, 1 plus the state 1, 0. That basically means if you measure one, you instantly know the state of the other. They're linked.
Still sounds pretty wild. So entanglement was confirmed. What happened next to actually get towards imaging?
Well, after Aspect's work, people started doing more experiments in quantum optics, really exploring these effects. A big milestone was the Hongo-Mandel experiment in 1987.
What did that show?
It demonstrated this really neat interference effect with two photons meeting at a beam splitter, a purely quantum effect. It showed the potential for using these quantum correlations.
Okay.
And that kind of work directly led to ideas like ghost imaging.
Ghost imaging sounds intriguing.
It is. It's a technique where you can actually create an image of an object using photons that haven't interacted with the object itself.
Wait, how does that work?
It relies on the correlations between entangled photon pairs. One photon might interact with the object, but you detect the other one. And by correlating the measurements of both, you reconstruct the image.
So you're imaging something without the imaging light even hitting it.
Sort of, yeah. It's based on the shared information in the entangled pair. And around this time, tools to describe these quantum light sources, like the non-classical correlation function G2 of tau, became really important.
Okay, I can definitely see why people are excited now. Ghost imaging, spooky connections. So, boiling it down, why does quantum imaging really matter? What are the big advantages Schneppat highlights?
Yeah, the essay points to several key benefits.
Yeah.
First off, just increased precision, better resolution.
Seeing smaller things.
Exactly. Using quantum correlations can push past those classical diffraction limits we talked about. Second, you can get reduced noise.
Cleaner images.
Right. Especially with faint signals. Quantum light sources, like entangled photons, can be inherently less noisy in certain ways than classical light.
Okay, better resolution, less noise, anything else?
The really exciting part, perhaps, is enabling completely new types of applications, like imaging through stuff that's normally opaque.
Through fog? Or other materials?
Potentially, yes. Or making incredibly sensitive measurements that weren't possible before.
So it's not just incremental improvements, it's opening new doors.
That's the idea. And this has huge implications, both for fundamental science, studying tiny things with more accuracy, and for society.
How so for society?
Well, think about medicine. Detecting tumors earlier, maybe with less harmful radiation, or security checking inside containers without opening them. It's about improving diagnostics, safety, quality of life through more precise tech.
Okay, that makes sense. We've mentioned entanglement quite a bit, but Schneppat's essay surely covers other key quantum ideas, right?
Yeah.
What are the other pillars here?
Definitely. Entanglement is huge, but not the only piece. Superposition is another one.
That's the being in multiple states at once thing.
Exactly. Like a quantum bit, or qubit, being both 0 and 1 simultaneously. Mathematically, you might write a state as psi I equals alpha 0 plus beta 1. This allows for processing information in parallel, in a way.
Okay.
Then there's non-locality, which is directly tied to entanglement. It's that spooky action measurements on one entangled particle instantaneously influencing the other, no matter the distance. Experiments violating Bell inequalities have confirmed this isn't just some hidden classical effect.
Still bends the mind a bit.
It does. Then, quantum randomness. Measurements in quantum mechanics are fundamentally probabilistic. You can't always predict the outcome with certainty.
That sounds like a downside.
You'd think so, but actually this randomness, the statistical nature of it, can be used in certain imaging schemes to help improve resolution. It's counterintuitive.
Huh. Okay.
And finally, there's quantum noise. Heisenberg's uncertainty principle, delta x, delta p, is greater than or equal to h bar over two fundamental limits on how precisely you can know certain pairs of properties.
Right. A fundamental fuzziness.
Yes. But even here, quantum mechanics offers tools. Using things like squeeze states or entangled states, you can sometimes manipulate this noise, reducing it for one measurement at the expense of another to optimize things.
So quantum mechanics gives you both the weird challenges, like uncertainty, and the weird solutions, like entanglement and superposition, to beat classical limits.
That's a good way to put it, yeah.
Okay, so those are the principles. What about the actual hardware? What technologies make quantum imaging possible? Schneppat must cover this.
He does. Key technologies are crucial. First, you need those quantum light sources we mentioned.
Like the entangled photons. How do you make those?
A common way is spontaneous parametric down conversion, or SPDC. You shine a laser into a special nonlinear crystal.
Like BBO. Bit variable rate.
Exactly. BBO is a popular one. And inside the crystal, a single high-energy photon can spontaneously split into two lower-energy photons that are entangled. Mathematically, you might describe the output state as an integral over frequencies, showing the correlations between the signal and idler photons.
Okay, so SPDC for entangled pairs. What about squeezed light?
Squeezed light is another type. It's light where the quantum noise in one property, like its amplitude, is reduced below the standard quantum limit. But the noise in another property, like its phase, increases to compensate. because of the uncertainty principle.
So you trade noise in one aspect for less noise in another.
Precisely. Useful for very sensitive measurements.
And detecting these single photons, or subtle quantum states, what do you use?
You need extremely sensitive detectors. Avalanche photodiodes, APDs, are one type. Superconducting nanowire single photon detectors, SNSPDs, are even more sensitive, capable of detecting individual photons with high efficiency.
Right, high-tech detectors. What about the optics?
You need precise optical setups. Interferometers, like the Mach-Zehnder type, are really important. They use superposition splitting and recombining light paths to make incredibly precise measurements, essential for things like quantum holography.
So it's a whole system. Special light, sensitive detectors, precise optics, non-linear crystals.
Exactly. It's a sophisticated toolkit.
And managing all the data that comes out. You mentioned algorithms. Are there specific mathematical tools that are key here?
Absolutely. The math is essential to interpret the results. One tool is the Wigner function.
What's that do?
It's a way to represent a quantum state in phase space, sort of like plotting its position and momentum characteristics simultaneously. It gives a visual way to see how quantum or classical a state of light is. It has a formal definition involving the wave function, W of x, P equals, well, it's an integral transform.
Okay, a way to visualize quantum states. What about putting the image back together from the measurements?
That needs specific reconstruction techniques. Bayesian algorithms are often used. They use probability theory to figure out the most likely image given the measurement data and any prior information you have. Think P of rho given D is proportional to P of D given rho times P of rho.
Using probability to reconstruct.
Right. And there are also iterative algorithms, like the Gertzberg-Saxton algorithm. These start with a guess for the image and then repeatedly refine it step by applying constraints based on the measurements you made. Very important for techniques like ghost imaging.
Makes sense. You need clever math to decode the quantum information. Okay, let's get to the really exciting part Schneepat covers, the applications. Where's this tech actually making a difference, or where could it?
The potential applications are really broad. Biosciences and medicine are a huge area.
Like seeing inside the body.
Yes, potentially. But also imaging living cells with incredible resolution. Techniques like super-resolution ghost imaging aim to get detail beyond the normal diffraction limit.
Better than a standard microscope.
Potentially, yes. And importantly, often using very low light levels. This is key for studying living cells without damaging them. It's like getting enhanced resolution, maybe represented by a modified uncertainty relation, like delta x, delta less than h bar, by using quantum correlations.
So, safer for live cell studies, what about diagnostics? You mentioned tumors earlier.
Right. The hope is for earlier tumor detection with much higher sensitivity and contrast, especially in difficult tissues, using entangled photons, and potentially achieving this with significantly lower doses of, say, radiation compared to some current methods.
That would be massive for patients. Okay, so medicine is big. What else?
Material science and nanotechnology. Quantum imaging can probe nanostructures, find tiny defects in crystal lattices, or characterize surfaces with amazing precision.
Ow.
Again, ghost imaging can be used. Analyzing the photon correlations that G2 function we mentioned can reveal information about the material structure. You can also characterize things like quantum dots or nanotubes, measure their optical or even mechanical properties using quantum interferometry.
So peering into the structure of new materials at the nanoscale, that sounds vital for developing new technologies.
It really is. Understanding materials at that level is key.
What about bigger scale things? Security.
Yes, security and surveillance is another promising area. The idea of imaging through opaque or scattering materials.
Seeing through walls. Maybe not quite.
Maybe not walls yet, but potentially through fog, smoke, or certain packaging materials. Correlation imaging techniques can help reconstruct an image even if the light path is scrambled.
Applications.
Think logistics, checking the integrity of goods inside sealed containers without opening them. Or security screening, potentially detecting hidden explosives or contraband using ghost imaging techniques at borders or checkpoints.
That non-invasive inspection capability sounds incredibly useful. It seems quantum imaging spans from the tiniest scales right up to practical security uses.
It does. And we shouldn't forget fundamental physics itself.
How does it help there?
Well, these techniques allow physicists to directly visualize quantum effects in experiments. You can design experiments to explicitly show things like Hungel-Mandel interference, or even try to image the Wigner function of a quantum state to demonstrate its non-classical nature.
Making the quantum world a bit more visible.
Exactly. And the high precision available allows for stringent tests of quantum mechanics itself, and could even help develop or constrain new physical theories beyond our current understanding, maybe pointing towards modifications of the Schrödinger equation or entirely new frameworks.
Wow, so it feeds back into understanding the very rules it operates by. Fascinating. Okay, looking ahead then, based on Schneppat's perspective, what's the future hold? Where is this all going?
Well, Schneppan suggests we'll see a strong push towards commercialization relatively soon. Medicine, the semiconductor industry, checking chips for defects and security seem like the frontrunners.
Real products based on this.
That's the goal. We might also see whole new fields emerge, like quantum biology, really digging into the quantum aspects of life, and expect continued advances in astrophysics and materials science, driven by better imaging tools.
And longer term, the big picture.
Longer term, the vision includes things like contributing to sustainability, maybe through more efficient resource discovery or environmental monitoring. And integration with the future quantum internet, imagine real-time sharing of quantum sensor data across secure networks.
A quantum-enabled world, in part powered by quantum imaging.
That's the kind of long-term potential people envision. But, Schneppet rightly points out, getting there requires a lot of continued effort.
Like what?
Interdisciplinary research needs to keep going strong. International collaborations are vital. And of course, sustained funding and support programs are essential to translate the lab research into real-world technologies.
It sounds like an incredibly exciting but also challenging road ahead. Okay, let's try and wrap this up. To summarize our deep dive, drawing heavily on Jörg Osha Schneppet's essay, what are the main takeaways for you?
I'd say the core message is that quantum imaging, by leveraging these unique quantum principles like entanglement and superposition, offers genuinely transformative improvements in how well we can see things, resolution, sensitivity, precision.
Right.
And its impact isn't narrow. It promises to be really broad, touching everything from fundamental science to practical applications in medicine, materials, and security. It's a fundamental shift.
Yeah, and as we've explored today, again, thanks to the insights in Jorgo Schneppat's work, it feels like quantum imaging isn't just a slightly better camera technology. It's more like a fundamental change in how we perceive and interact with the world at its deepest levels.
Well put.
It really holds the promise of unlocking discoveries and technologies we probably can't even properly imagine right now.
That's the exciting part.
We certainly hope this deep dive has sparked your curiosity. It's a field moving incredibly fast, and there's always more to learn. Maybe consider digging a bit deeper into those core ideas yourself, superposition, entanglement. They really are the heart of it all.
Absolutely. Understanding those is key.
Thank you for joining us for this quantum deep dive based on the insights from Jorgo Schneppat's essay.
Thanks for the conversation.